All right, the next algorithm we're going to look at is insertion sort. Like the other algorithms we've seen, it partitions the array into sorted and unsorted partitions. But this time, the implementation I'm going to show you grows the sorted partition from left to right. So it grows the sorted partition from the front of the array. So how does insertion sort work? Well, it starts out by saying that the element at position 0 is in the sorted partition. And because the sorted partition is of length 1, by default, the element is sorted. Because if you have an array of length 1 or a partition of length 1, it's sorted, right? There's only one element. So at the beginning, the elements from position 1 and to the right are in the unsorted partition. And so we're going to set a first unsorted index field to 1. Now, on each iteration, we take the first element in the unsorted partition, which will be the element at array of first unsorted index, and we insert it into the sorted partition. And so at the end of each iteration, we'll have grown the sorted partition by 1. And so what we'll do on the first iteration is we'll take 35, because that's the first unsorted value, and we will insert it into the sorted partition. And at the end of the iteration, the first two elements in the array will be sorted. So how is each element inserted? Well, what we do is we compare the value we're inserting with the values in the sorted partition, and we traverse the sorted partition from right to left, and we look for a value that is less than or equal to the one we're trying to insert, because once we find that value, we can stop looking. We have found the correct insertion position for the new value that we're trying to insert. Because remember, when we're inserting the value, we are working within the sorted partition. And so if the element at index I in the sorted partition is less than or equal to the element we're trying to insert, then all of the values to the left of element I will be less than or equal to the value we're trying to insert, because all the values are in sorted order. So as we look for the correct insertion position, we shift values in the sorted partition to the right. And you'll see this in action right now. Let's go through this by hand. So on the first iteration, we're going to assign 35 to a new element field, because 35 is the first element in the unsorted partition. And then we use I to traverse the sorted partition from right to left. So we compare 35 to 20. Now 35 is greater than 20, so 35 is already in its correct position in the sorted partition. It's not in its correct position in the array, but it is in the sorted partition. So after the first iteration, the sorted partition has been grown to 2, length 2, and the first two elements are in their correct position. And now the first unsorted index is at index 2, and I is assigned 1, because that's the rightmost index in the sorted partition. So we assign minus 15 to new element, and now we need to insert minus 15 into the sorted partition. So we compare minus 15 against 35. Minus 15 is less than 35, and so we want to shift minus 15 down the array, but another way of looking at it is we're going to shift 35 to the right to make room for minus 15. And so we assign 35 to position 2. Now don't worry that we've overwritten minus 15, because we have it saved in a new element field. So now we're going to compare minus 15 to 20. Minus 15 is less than 20, so we're going to shift 20 to the right to make room for minus 15. And at this point, we've hit the front of the array, so we have nothing else to compare minus 15 to. Basically, we have the smallest element in the sorted partition, and because we've hit the front of the array, this is where we're going to insert minus 15, and so we go ahead and do that. And we've ended the second iteration, and at this point, we've grown the sorted partition to 3, and the first 3 elements in the array, which is the sorted partition, are in their correct positions in the sorted partition. So now the first unsorted index is at position 3. So we're going to assign the value of 7 to new element, and we're going to compare 7 against 35. 7 is less than 35, so we're going to shift 35 to the right. We compare 7 against 20. 7 is less than 20, so we're going to shift 20 to the right. And then we compare 7 against minus 15. 7 is greater than minus 15, so we have found the insertion position. Remember, we're working within the sorted partition. So if there was anything to the left of minus 15, all those values would be less than minus 15. So there's no need to keep traversing the sorted partition. The moment we hit an element that's less than or equal to the one we're trying to insert, we've found the correct insertion position. And so we're going to insert 7 into position 1, and we have completed another iteration. We've grown the sorted partition by 1, and all of the elements in the sorted partition are sorted. So the next element we're going to want to insert is 55. So we compare 55 against 35. 55 is greater than 35, so we've already found its correct position. And so we completed this iteration, and now the first 5 elements in the array are in their correct sorted position. Now I'm not going to go through 1 and minus 22 because 1 is going to get shifted all the way down to position 1, and then minus 22 will be shifted all the way down to position 0. So I won't bore you with slides doing that. I think at this point, you get the gist of the algorithm. And so that's insertion sort. It starts out by saying the first element is sorted. The implementation, or at least the implementation that I'm going to show you, does that. It grows the sorted partition from left to right. And on each iteration, it picks off the first element in the unsorted partition, and it inserts it into the correct position in the sorted partition. And it does that by shifting elements to the right to make room for the new element. So insertion sort is an in-place algorithm. We don't need to create any temporary arrays. We have a few extra fields, but as I've said before, as long as the extra memory we're using doesn't depend on the number of items we're sorted, it's an in-place algorithm. It's a quadratic algorithm, and it's a stable algorithm. It's stable because when we're picking off elements, we're doing that from left to right. So if, let's say, there are 2 9s in the array, we're going to insert the leftmost 9 first. And then when we come to the rightmost 9, remember that when we're looking for the insertion position, we stop when we hit an element that is less than or equal to the one that we're inserting. So when we're inserting the 9, we're eventually going to hit the first 9 we inserted into the sorted partition, and that second 9 will be inserted to the right of the first 9. And so the relative positions of those 2 9s will be preserved. And so insertion sort is a stable sort algorithm. Okay, so that's an explanation of insertion sort, and we've gone through the implementation I'm going to show you. So let's get on to coding that implementation. I'll see you in the next video.